Hello, and thank you for attending this talk. My name is Geert Heijman, and I'm a researcher at Nokia Bell Labs. I am part of a team that researches the future of software development and creates prototypes of future software development tools. I will present joint work with my colleagues Raf Huizegems, Pascal Justen, and Tom van Kutsen. I will introduce our new vision called Natural Language Guided Programming and explain how we made a first prototype to validate this vision. Let me start this talk with an observation. Nowadays, programmers rarely implement projects from scratch. For example, data scientists won't implement a machine learning model in plain Python or C, but they instead will use libraries like TensorFlow, PyTorch, scikit-learn, and so on. And there are also many libraries for data visualization, data analysis, numeric computational, parallel data processing, and so on. And even for very dedicated tasks like displaying a progress bar, you could save time if you know the right library and if you know how to use it. But because there are so many libraries and APIs out there, it's very hard to keep up. Programmers are spending more and more time in their browser figuring out how to use a library. What would be ideal if there was a library expert to which developers could ask questions, and that expert would then take a look at their code and explain to the developer with a few lines of code how to solve the problem. Of course, having such a human expert would be very expensive. But what if the expert was an AI? We believe that with recent progress in machine learning and natural language processing, that this could become a reality. And this is the topic of our work. Let me illustrate this vision with an example. A developer is coding a Python script to analyze a bit of data. And this developer has created a list called query lengths. So it's not important to understand the implementation details of the code here, but the developer basically created a list of positive integers and now wants to create a histogram based on this list. In our vision, the developer could ask an AI how to do this, and the AI would respond with a code snippet. The question can be formulated in plain English as an inline comment, and will be interpreted by the AI in the context of the code that was already written. So as you can see here, the response of the AI is contextualized because it uses the query length variable that was in the developer's code, and also attempts to provide sensible names for the axis and title. We call this practice Natural Language Guided Programming, or NLGP for short, and we refer to the AI as the NLGP assistant. To validate our vision, we created prototypes for an NLGP assistant. The key technology that we use for making these prototypes is language modeling. Language models have many applications, but in this context it is relevant that a language model is a technique to generate text. Conceptually, a language model is trained to guess the next word or token in a sequence. For example, given the sequence "the cat sat on," a language model could predict that "the" should be the next word. We can then predict an entire sentence or text by iteratively adding the predicted word to our sequence and then predict the next word each time. Formally, a language model estimates the conditional probability of a word given the previous words in the sequence. And using a search strategy, you can generate text. One search strategy, for instance, would be greedy search, where for every word you predict, you each time select the most likely word according to the language model. The language model that we will use is GPT-2. The GPT-2 model was proposed by OpenAI and was one of the first models to generate realistic coherent text. It is a neural network that was trained on 40 gigabytes of text that was scraped from web pages. An interesting property of GPT-2 and other similar models is that it can be adapted to different domains. GPT-2 has a general understanding of text, and when you would further train it on a different domain, for instance with song lyrics data, the model will be able to generate new song lyrics. This concept is known as fine-tuning, and typically it works much better than training a model from scratch on only the song lyrics data. To create an NLGP assistant for Python, we applied the same idea, but instead of using song lyrics data, we fine-tuned GPT-2 with code. And because for our model it is crucial to learn a mapping from natural language to code, we want to make sure that the code is interleaved with enough descriptive comments. We therefore chose to create a dataset from Jupyter Notebooks. Jupyter Notebooks were designed to interleave markdown descriptions with code, and therefore we expect that they are a good data source for our task. For our training dataset, we used close to 300,000 notebooks that were scraped from GitHub projects with permissive licenses. Before feeding the notebooks to the model, we do some pre-processing, which I will explain in the next slides. The first bit of pre-processing concerns the comments. As mentioned, good descriptive comments will be key for creating our assistant. And we trained 3 different models which differ in how the comments are obtained. On the left, you see a model that is trained on what we call natural comments, meaning that we just use whatever comments or markdown descriptions were available in the original notebooks. However, for domains where code is not annotated with a lot of inline comments, it is useful to have another source for descriptions. So what you see in the middle is that we trained a model where we first stripped all the original comments from the notebooks and then automatically insert comments that are extracted from the documentation of calls. For example, above the instantiation of the k-means object, we inserted the docstring from the k-means class. Similarly, we insert the docstring of the .fit call. This required for us to build tooling to statically link function calls to their definition. And then finally, on the right, as a baseline, we train a model on data without any comments. This will enable us to measure how predictive code is without any natural language intent. Next, we convert notebooks to Python code. While doing this, we also add special symbols that inform the model about the structure. We use 2 special symbols, which are shown in blue in the code snippet on the right. There is a special cell symbol to encode the end of every cell in the original notebook. In this example, there are 2 cells, and at the end of each of them, you will see the special cell token in blue. Then we also add a special symbol at the end of every comment. If there are multiple inline comments following each other, we only add the symbol at the end of the last inline comment. These symbols are used during prediction. The end of comment symbol will be inserted after the comment that expresses the user intent. And this way we communicate to the model that it should start to predicting code instead of trying to further autocomplete the comment itself. Then the end of cell token is used as a stopping criteria. So in theory, we could use a language model to predict hundreds of lines of code, but that wouldn't be very useful. For our prototype, we will keep on predicting code until the model predicts the special end of cell token. After we had trained our models, we of course wanted to know how useful the models were. We had a collection of a few thousand notebooks that were not used for training, and after using the same pre-processing as for training, we could evaluate how well the models could predict these notebooks. Cross-entropy is a standard metric for this, and on these 3 plots you can see as training progresses that the model becomes better and better at predicting these notebooks. But of course, this still doesn't tell us much about how useful the models will be for creating our NLGP assistant. To evaluate this, we first needed to create a benchmark with representative test cases. So we took the notebooks that were not used for training and with a few heuristics find candidate test cases from these notebooks. Each test case consists of context code, a natural language intent, and target code. To mine the candidates, we automatically extract the short English comments from these notebooks, and these comments will then be the candidate's intent, and the preceding code will be used as the context. In a second step, we manually reviewed 600 candidate test cases with a team of 9 annotators with all a background in Python. On the right, you see a screenshot of the annotation tool that the programmers used. First, the programmers had to decide whether a comment was indeed describing the code that followed it. They had the option to slightly rephrase the candidate intent if necessary. 200 out of 600 candidates were accepted as relevant test cases. To annotate the target code, the programmers had to mark a fragment in the candidate target code in blue. At the end of the process, we had 200 test cases that were derived from notebooks from GitHub projects that we didn't use for training. Next, we used our tree models to predict code for each test case. So given the context and intent, the models generated a piece of code that hopefully is similar to the target code. In the next step, 10 programmers had to rate these predictions against 4 categories: usefulness, precision, coverage, and compatibility. Usefulness is the most important aspect and measures how useful a prediction is for addressing the intent of the test case. To avoid bias towards a certain model, the annotation process was blind in the sense that the annotators could not see the model names and the predictions were presented in a random order. Each programmer was given a subset of the test cases, so on average we ended up having 4 ratings per prediction. In this plot you see a summary of the ratings with respect to the usefulness of the predictions. The y-axis shows the 3 models, and the colors of the bars represent 4 different levels of usefulness the annotators could choose from. So on the statement, the predicted code is useful for implementing the intent, they could answer strongly disagree, disagree, agree, or strongly agree. We can see that for both the doctrine model and the natural model, roughly 2/3 of the predictions were considered useful or highly useful. This indicates that they are decent first prototypes of an NLGP assistant. The natural model comes out the best out of the test, but the doctrine model performs surprisingly well considering the repetitive nature of the comments it was trained on. At the same time, the poor ratings of the no comments model show that the natural language intent is really crucial to having useful predictions. It is not sufficient to create an assistant that merely guesses your intent based on your previous code alone. Recently, GitHub released Copilot in beta, and OpenAI made Codex available behind the REST API. These two systems are closely related to our vision, so let me quickly explain how they relate to our work. Both Copilot and Codex can be seen as NLGP assistants, and their underlying models have a similar architecture as the GPT-2 model that we fine-tuned. Except these models operate on a much larger scale. The Codex model has at least 33 times more parameters and was trained on 84 times more Python data. We can therefore expect that Codex is more general purpose and that its prediction quality should also be better. This was also confirmed by a preliminary evaluation that we did of Codex on our benchmark. However, the comparison was a bit tricky because we saw from Codex predictions that it had clearly seen some of the test cases during its training. It could recite those test cases from memory. Of course, this bigger scale also comes at a cost. Training a model like Codex is very resource intensive, and even making predictions will require a lot of computational power. For our prototypes, it's still feasible to run them on a normal machine, but it's not the case for Codex or Copilot. To sum up, we saw a need and an opportunity for smart tools that help developers with correctly using the right API. We think that the creation of these tools should not only be driven by machine learning researchers, and therefore we wanted to share this vision in this community and wanted to demonstrate how first prototypes for such assistants can be built without using a lot of computational resources per se. We hope that this work can therefore be a stepping stone for others, and at the end of our paper we include a research agenda with topics for further research. We also share our benchmarks, the human ratings we assembled for our evaluation, and we release the models. Thank you for listening.